Welcome to Suchitra's Statistics classes. Today we are going to discuss about geometric distribution. The geometric distribution represents the number of failures before you get a success in a series of Bernoulli trials. Theoretically, there are an infinite number of geometric distributions. The value of any specific distribution depends upon the value of probability P. Then let us think about the assumption of a geometric distribution. There are three assumptions for a geometric distribution. There are two possible outcomes of each trial, success or failure. That is, it is a Bernoulli trial. The trials are independent. The probability of success P is the same for each trial. Consider a Bernoulli sequence of trials with probability of success P. So the probability of failure is 1 minus P or Q. That is P of S equal to P and P of F equal to Q. Let X be the number of failures before the first success in a series of independent trials. Here X takes the value 0, 1, 2, 3, etc. up to infinity. Therefore, P of X equal to 0 is P of 0 failures before the first success, that is P of S, that is P of success is equal to P. P of X equal to 1 is probability of one failure before first success, that is P of Fs. And we know that trials are independent. It is P of F into P of S, that is QP. P of X equal to 2 is equal to P of probability of two failures before first success, that is P of FS. Again, trials are independent, so we can rewrite that as P of F into P of F, that is Q squared P and so on. And P of X equal to small x is probability of small x failures before the first X, that is P of small x F's and 1s, that is Q raised XP. Therefore, the PDF of X is F of X equal to Q raised XP, where X takes the value 0, 1 to infinity and equal to 0 elsewhere. The distribution gives the probability that there are 0 failures before the first success, probability that there are 1 failure before first success, probability there are 2 failures before the first success, and so on. Since the PMF forms a geometric sequence, the distribution is called as geometric distribution. Now let us define what is meant by geometric distribution. A discrete random variable said to follow geometric distribution if its PMF is f of x equal to q raised xp for the values of x is from 0 to infinity and equal to 0 elsewhere, q plus p equal to 1 and 0 less than p less than 1. Now let us discuss about the moments. Mu1 dash, first order raw moment, is equal to E of x equal to summation over x of x, which is from summation from 0 to infinity x q raised to x p. Since f of x is q raised to x p and range of x is from 0 to infinity. And take p outside, p into summation 0 to infinity x q raised to x. Put the various values of x in the function, we will get p into 0 into q raised to 0 plus 1 into q raised to 1 plus 2 into q square plus 3 into qq plus up to infinity, which is equal to p of 0 plus q plus 2q square plus 3q plus etc. Take a q outside from this one. So we have pq into 1 plus 2q plus 3q square plus etc. And we know that 1 plus 2q plus 3q square plus etc. is equal to 1 minus q raised to minus 2. Therefore, it is equal to pq into 1 minus q raised to minus 2. And what is 1 minus q? 1 minus q is p. So, that becomes pq into p raised to minus 2, that is qp raised to minus 1, that is q by p. So, mu 1 dash, that is mean equal to q by p. Therefore, the mean of a geometric distribution with the probability density function q raised to xp is q by p. Then let us think about the second order row moment, that is mu 2 dash, which is equal to e of x square equal to summation over x square fx. That is summation from 0 to infinity x square q raised to x p. Take a p outside, so we get p into summation 0 to infinity x square q raised to x. Substitute the values of x in the summation, you will get p into 0 square q raised to 0 plus 1 square q raised to 1 plus 2 square q raised q square plus etc. P into q plus 4q square plus 9q plus 16q raised to 4 plus etc. And take a q outside, so you will get pq into 1 plus 4q plus 9q square plus 16q cube plus up to infinity. We are going to rewrite 1 plus 4q plus 9q square plus 16q cube in the following manner. That is, first part is 1 plus 3q plus 6q square plus 10q cube plus etc. Already we have 4q, so we will have a q here. Then we have 9q square, so we write 3q square here. We have 16q cube, so we will write 6q cube here plus etc. So, second part is this one. And we know that 1 plus 3q plus 6q square plus 10q cube plus etc. equal to 1 minus q raised to minus 3. The first part is already 1 minus q raised to minus 3. And from the second part, we take a q outside and the term inside the bracket is again 1 minus q raised to minus 3. So, we get the expression like this. And we know that 1 minus q is p. So, we have that is q by p square plus q square by p square. Therefore, mu 2 dash is q by p square plus q square by p square for a geometric distribution with the probability density function q raised to xp. Variance equal to e of x square minus e of x whole square, that is mu 2 dash minus mu 1 dash square, which is equal to q by p square plus q square by p square minus q by p whole square, which is equal to q by p square. Therefore, variance mu 2 equal to q by p square. Therefore, standard deviation sigma is equal to root mu 2 is equal to root q by p. Then let us think about the moment generating function of geometric distribution. We know that mxt is expectation of e raised to tx. That is summation 0 to infinity e raised to tx fx. That is summation 0 to infinity e raised to tx q raised to xp. Combine this e raised to tx and q raised to x together, we will get summation 0 to infinity q e raised to t all raised to xp. Take the p outside, we will get p into summation 0 to infinity q e raised to t all raised to x. Substituting various values of x in the expression, you will get p into q e raised to t all raised to 0 plus q e raised to t all raised to 1 plus q e raised to t all square plus etc. up to infinity. That is p into 1 plus q e raised to t, q e raised to t all square plus etc. which is p into 1 minus q e raised to t all raised to minus 1. 1 plus q e raised to t all raised to 1 plus q e raised to t all square plus etc. up to infinity is 1 minus q e raised to t all raised to minus 1. So we have p by 1 minus q e raised to t. Therefore, moment generating function mxt of geometric distribution is p by 1 minus q e raised to t. Differentiating the moment generating function successively with respect to t and putting t equal to 0, we get mu 1 dash, mu 2 dash, mu 3 dash, mu 4 dash, etc. Hence, we can calculate mu 2, mu 3, mu 4, etc. Then there is an alternative form for geometric distribution. Geometric distribution is redefined by some authors as x takes the value 1, 2, 3 up to infinity. So far we have the values of x are 0, 1, 2, 3, etc. Here x takes the value 1, 2, 3, etc. Here x is the number of trials needed for attaining the first success. In the previous model, x is the number of failures before the first success. Here x is the number of trials needed for attaining the first success. So the PDF of this form is f of x is q raised to x minus 1p, x takes the value 1, 2, 3, etc. p plus q equal to 1. There e of x equal to 1 by p, v of x equal to q by p square, and mxt is equal to p e raised to t divided by 1 minus q e raised to t. Now let us study the famous property, that is memoryless property or lack of memory property. Now let us discuss what it is. Memoryless property means that a given probability distribution is independent of its history, that is, its trials is independent of the previous trials. Any time may be marked down as time 0. If a probability distribution has the memoryless property, the likelihood of something happening in the future has no relation to whether or not it happened in the past. The history of the function is irrelevant to the future. Then some examples are tossing a coin is memoryless. Independent failures of a computer hardware follows memoryless property. Failure of hardware is independent of the fact that it hasn't failed for last 2 years. Now let us study the technical definition of lack of memory property. A discrete random variable x is memoryless with respect to the value of the variable, say a should be greater than 0, if the probability that x is greater than a plus b is also greater than 0, given that x is greater than a is simply the probability of being greater than b. Symbolically we can write p of x greater than a plus b given x greater than a is equal to p of x greater than b. Then a continuous random variable x over the range of real numbers is memoryless if for every real s and t, p of x greater than s plus t given x greater than t equal to p of x greater than. Now the geometric distribution possesses memoryless property. That is, if x has geometric density with parameter p, then p of x greater than or equal to s plus t given x greater than or equal to s equal to p of x greater than or equal to t for s and t varies from 0 to infinity. Now let us prove it. Let us take the LHS. LHS is p of x greater than or equal to s plus t given x greater than or equal to s. From the conditional probability, we can rewrite this as p of x greater than or equal to s plus t intersection x greater than or equal to s divided by p of x greater than or equal to s. The numerator is nothing but p of x greater than or equal to s plus t. Therefore, LHS become p of x greater than or equal to s plus t divided by p of x greater than or equal to s, which is equal to summation s plus t to infinity q raised to x p divided by summation s to infinity q raised to x p. P and p get cancelled. We have q raised to s plus t plus q raised to s plus t plus 1 plus q raised to s plus t plus 2 plus etc. divided by q raised to x plus q raised to s plus 1 plus q raised to s plus 2 plus etc. From the numerator, take q raised to s plus t outside, and from the denominator, take q raised to s outside. We will have this expression. So this is equal to q raised to s plus t by q raised to s, which is equal to q raised to t. Now let us take RHS in this format and take a p q raised to t outside. We will have this expression. Since 1 plus q square plus etc. equal to 1 minus q raised to minus 1. So we have RHS equal to q raised to t. Therefore, LHS equal to RHS. So geometric distribution possesses memoryless property. Using moment generating function, show that the distribution of x1 plus x2 is given by the probability function p of x equal to x plus 1 into p square q raised to x. Given that x1 follows geometric distribution, then mx1t is p into 1 minus q e raised to t all raised to minus 1, and x2 follows geometric distribution, then mx2t is equal to p into 1 minus q e raised to t all raised to minus 1. Since x1 and x2 are independent by the property of moment generating function, we can write as m of x1 plus x2t is equal to mx1t into mx2t. That is p into 1 minus q e raised to t raised to minus 1 into p into 1 minus q e raised to t minus 1, which is equal to p square into 1 minus q e raised to t raised to minus 2. Now, if the probability function of a random variable x is x plus 1 p square q raised to x for the values of x equal to 0, 1, 2, etc., its moment generating function mxt is expectation of e raised to t, that is summation over x e raised to tx fx, that is summation from 0 to infinity e raised to tx x plus 1 p square q raised to x, since it is its probability density function. And take p square outside and combine q raised to x and e raised to tx together, we will get p square summation 0 to infinity x plus 1 into q e raised to t all raised to x. Substitute various values of x into it, we will get p square into q e raised to t all raised to 0 plus 2 into q e raised to t all raised to 1 plus 3 into q e raised to t all square plus etc. That is p square into 1 plus 2q e raised to t plus 3q e raised to t all square plus 4q e raised to t all cube plus etc. That is p square into 1 minus q e raised to t raised to minus 2. Hence, by the uniqueness theorem, x1 plus x2 follows a distribution with the probability density function f of x equal to x plus 1 p square q raised to x for the values of x varies from 0 to infinity. Then let us think about the example 3. Let x be a discrete random variable having the PDF f of x equal to 2 raised to minus x. X takes the value 1, 2, 3, etc. Obtain its moment generative function, hence find mean and variance. We know that f of x is 2 raised to minus x. So mxt is summation over x e raised to tx fx, summation from 1 to infinity e raised to tx 2 raised to minus 2, that is summation from 1 to infinity e raised to t by 2 all raised to x. Substitute various values of x there, we will get this expression. Take e raised to t by 2 outside, we will get this expression. So this is equal to e raised to t by 2 into 1 minus e raised to t by 2 all raised to minus 1. Then we will get moment generating function mxt equal to e raised to t divided by 2 minus e raised to t. Now we want to find mean and variance. How we can find mean and variance from moment generating function? By successive differentiation of moment generating function with respect to t and putting t equal to 0, we can calculate mu1 dash, mu2 dash, mu3 dash, etc. Thereby mu2, mu3, etc. Now we are going to differentiate mxt. For that one, we will rewrite mxt as, we know that mxt is e raised to t by 2 minus e raised to t. We will rewrite that as 1 by 2 e raised to minus t minus 1. So first order derivative mx dash t is this one. Then mean mu1 dash is equal to mx dash t at t equal to 0, which is equal to 2. Then mx2 dash t will be like this. Putting t equal to 0 in mx2 dash t, we have mu2 dash, which will be 6. So variance mu2 equal to mu2 dash minus mu1 dash square, which is equal to 2. Now let us summarize what we have studied today. If PDF is f of x equal to u raised to x p, then mean equal to q by p, variance equal to q by p square, and moment generating function equal to p by 1 minus q e raised to t. If f of x is q raised to x minus 1 p for various values x is from 1 to infinity, mu1 dash is 1 by p, mu2 is q by p square, and mxt is p e raised to t divided by 1 minus q e raised to t. And geometric distribution possess memoryless property, that is p of x greater than or equal to s plus t given x greater than or equal to s equal to p of x greater than or equal to t where s and t are greater than 0. Thank you for watching. If this is found to be useful, then like and subscribe Suchitra's statistics classes.